presenter of today's session. The next session is by Poulami Ghosh, who is currently doing BSc at Bethune College, Kolkata, who has attended MPTS level O. And Poulami Ghosh will be talking about transporting of structure of vectors.
Hello everyone. First of all, happy Independence Day to all. My topic is transport of structure of vector spaces. What is my aim of doing this? If X is any infinite set you have, then can we give it a vector space structure? This is my aim to see, is it possible or not? Before that, I want to give a small introduction that what is a vector space. A non-empty set V is said to be vector space over a field F if there exists a binary operation from V cross V to V. We called it addition. It's defined by X comma Y, where X and Y both come from V. Then this pair X comma Y, it will belongs to V cross V, and it is defined by X plus Y. And a dot, or it is called a scalar multiplication. It is defined from F cross V to V, defined by alpha comma X, where alpha is belongs to F and X is belongs to V, and it is defined as alpha dot X. It is called scalar multiplication. If V with these two operations is said to be a vector space if it follows some properties, that is X plus Y equals to Y plus X. This is commutativity for addition. X plus Y plus Z will be equals to X plus of Y plus Z. It is called associativity. If there exists 0 belongs to V for all X belongs to V such that X plus 0 is equal to X equals to 0 plus X. This is known as existence of identity. For every X belongs to V, there exists Y belongs to V such that X plus Y is equals to 0 equals to Y plus X. This is existence of inverse for each element of V. And if alpha belongs to F and X and Y both belongs to V, alpha dot X plus Y is equals to alpha X plus alpha Y. It is known as distributive property of multiplication over addition. If alpha and beta both are from F, the alpha plus beta dot X is equals to alpha X plus beta X, and alpha beta X is equals to alpha into beta X, and last 1 dot X is equals to X. So these are following condition which have to satisfy by a vector space. So there is some example of vector space. First, we know that Rn over R is a vector space with respect to usual addition and scalar multiplications. Similarly, Q plus dot Q is a set of all rationals is a vector space over addition and our scalar multiplication. In general, if F is any field, it will be a vector space over F with respect to usual addition and scalar multiplication. Similarly, the set of all n by n matrices which entries are from real number, it is also a vector space over R for usual addition and scalar multiplication. Here Pnx, this is the set of all polynomials of degree less than equals to n, is a vector space over R for addition and scalar multiplication. Now there are some examples which are not a vector space. First, I have the set of all positive reals. It is not a vector space over R for addition and scalar multiplication. Why it is not? If you see that it does not have that identity element, it does not have 0. So it violates one of those conditions. So it will not be a vector space. Similarly, the set of all primes over Q, it is also not a vector space for addition and scalar multiplication. Suppose I take any two elements from P, that is 3 and 5. If we add them, I will get 8, and it's not a prime, so it does not belong to here. So it violates one of those conditions, so it will not. And similarly, you can think about that why it is not. Okay, so now what is my goal? I want to see that we already see some vector spaces over usual addition and multiplication. So can we get some another operation which is not our usual addition and scalar multiplication, but still can I give a set of vector space structure? This is my aim. If it is possible, then we will see that how can we do that. Now suppose I have capital X is any infinite set. Can we give it a vector space structure? So here arise two conditions. If X is infinite, then it must be countable or uncountable. So I will break it into two cases. First one, I consider X as countable set. Now what is a countable set? If X is a countable set, then there will be a bijection from the set of all natural numbers. So a set is said to be countable if it has a bijection from set of all natural numbers. Since we know that Q is countable, right? So here X is countable, so it has a bijection from natural numbers, and also Q has a bijection from natural numbers. So I will surely get a bijection between X to Q. I here taken F as that mapping which is bijection from X to Q. Q plus dot has a vector space structure over Q. We already see that. Now I take any 2 points in capital X, that is small x and small y. Since there is a bijection, I will definitely get an image of X in Q. Here it is Fx. And similarly, I will get an image of Y in Q, that is Fy. You see that Fx and Fy they both belongs to Q, and Q is a vector space. So definitely Fx plus Fy, it also belongs to Q, right? Yeah. So since F is a bijection, then there will be an inverse of F that will be defined from Q to X. See, since Fx plus Fy, it belongs to Q, then I will get a pre-image of this point here in X. That is F inverse of Fx plus Fy. I defined as it X plus Y. And if X belongs to Q and C is from Q, then C dot Fx, it must be belongs to Q because Q is a vector space, so it will belongs to there. And similarly, there will be a pre-image of C dot Fx in X, and that is F inverse of C dot Fx, and we name it C dot C or scalar multiplication with X. So you please remember these two forms. Now my claim is with X will be a vector space over Q for these two addition and scalar multiplication. But I need to check that X satisfies all those conditions for a vector space for these two operations. First, we are checking for associative property. So we take any 3 elements from capital X, that is X, Y, and Z. Now we need to check that this is holds or not. So in first, we write here X plus Y plus Z. And in first case, we apply the operation between X and Y. So I will get F inverse of Fx plus F of Y. This is how we define our addition here. And for easy computation, I take it as P. So it will be P plus Z. Now again, I will apply the operation and I will get F inverse of F of P plus F of Z. Now what will be F of P? You see that F of P is F compose F inverse of Fx plus Fy. Now, F compose F inverse is nothing but the identity map So it will give me f of x plus f of y. So I get this result here. And in the second part, I use the binary operation between y and z. So what I get x plus f inverse of fy plus fz. Now for again easy to compute, I take it as q, and again I apply the operation between x and q, and I get f inverse of fx plus fq. And what will be my fq? Fq is f compose f inverse of f of y plus f of z. And since f of compose f inverse, it is an identity map, it will give me f of y plus f of z. So the result over here and in previous case, both are same. So it means with respect to this addition, associative properties hold. In the second part, we need to check is there exists any identity element. So we are taking an E belongs to X such that it follows the condition for an identity element. That is X plus E is equals to X equals to E plus X. Now I apply the operation between X and E and I get F inverse of Fx plus F of E is equals to A. Again, I take F composed from the both side and I get F of X plus F of E is equal to F of X. Now from here, I get F of E is equal to 0. It implies that E is equals to F inverse of 0. So this is my identity element in X. Now in the second, we need to check is inverse exist for all elements. So here I take X belongs to X and I take capital small y belongs to X such that X plus Y will be equals to E. Then I apply X and the operation between X and Y and I get F inverse of Fx plus Fy is equals to E. That gives, since I know that what is my f of e, that is 0, right? After apply f compose to the both side, I get f of x plus f of y equals to f of p. Because f of e is 0, I put it there. And finally, I get that y is equals to f inverse of minus of fx. So this is my inverse element of x belongs to x. Now we need to check that is this follow the commutative property or not. So first I take x plus y and see it gives me f inverse of fx plus fy, and y plus x gives me f inverse of f of y plus f of x. Since f of y and f of x are both belongs to q, right? And in q addition is commutative. So I can write f of y plus f of x as f of x plus f of y. So you can see that in both cases the result is same. So it is commutative also. Now similarly, you can check other properties as well. Now here is some example. What is the advantage of constructing such operation? You see, previously we see that the set of all primes is not a vector space, but you now see that we can find some operation such that we can make the set of all prime a vector space over Q. Similarly, say xn be any sequence, then xn you can find some operation such that xn will be a vector space over Q. Now here is case 2. What if x is uncountable? If x is uncountable and if you get a bijection from x to r, then by similar argument you can find some operations such that this set x will be a vector space over Q over R. Here I take an example, that is I define a mapping from F from set of all positive reals to R. It is defined by f of x is equal to log x, and it's a bijection. Then f inverse from R to R plus will be exist, and f inverse is equals to e power x. Now I need to find this what will be these two operations. So first I take x comma y belongs to R plus, and how we defined x plus y, that is f inverse of fx plus fy. So what is my fx? That is log x. And what is fy? That is log y. And log x plus log y, that will be log xy. So f inverse of log xy, that is e power log xy, and it will give me xy. And if I take any c from real numbers, then c dot x, that will be f inverse of c dot fx. Since fx is log x, then c dot fx, that will be log of x power c. And there is an f inverse, so it will be e to the power log of x power c. And it will give me x to the power c. Now, if I define x plus y such that x, y, and c dot x, that scalar multiplication, as x to the power c, then you see that R plus, it will be a vector space over R for these two, addition and scalar multiplication. And similarly, you previously see that R plus is not a vector space over R, but now we can construct such operation such that R plus will be a vector space. So I find it is really a strong result that we can make any x a vector space over a suitable field. Now there is an observation, that is, you can similarly do this procedure for groups. If V is a set and you are able to make it a vector space, so you see that it is already a groups and abelian groups for these plus operations. And there is two questions from my side, that is, does there exist any addition and scalar operations such that P is the set of all prime numbers, P plus dot become a vector space over R? You definitely think about that. And there is one more question, that is, we already know that Q is a vector space over Q for addition, our usual addition and scalar multiplication. But my question is how we construct whatever we do. So can we find some other addition and scalar multiplication which are not similar to our usual addition and scalar multiplication and give you another vector space structure? Thank you.